Greetings, everybody. Time for another optimization problem. And here's how this one goes. It says that by airline policy, that baggage must be box shaped. And here already to start the problem, I've drawn a box to represent a piece of luggage. And, who knows why this is the airline policy and how they get the numbers and so on. But the policy is, according to this question, that the sum of the length, width, and height of the box can't exceed 144 inches. Okay? All right. What are the dimensions and volume of a square-based box that once again represents the luggage with greatest volume under these conditions? So the impression that we get from the question is, well, there are lots of different shaped boxes, some taller, some wider, that satisfy this criterion that the sum of the length, width, and height can't exceed 144 inches, but only one of them fits the greatest volume on the inside. What you might imagine is like a really tall but narrow box is not going to hold as much space on the inside of it as one that might be a little shorter but wider. Okay, so there's an optimum. There's a way to optimize it. So here's how I would go through the problem. I noticed that this one has some prompts in several parts, but let me say it like this. If our objective is to maximize the volume of a box like this, and I've drawn a box with a square base, okay, notice on the base this side's W and this side's also W, because a square is a rectangle where every side is the same. Okay, so W, W, W all the way around the bottom, and H is its height. Okay, so I've drawn that just for the sake of your imagination if you want to see it. We want to maximize that, and I need a formula for maximizing the volume. Okay, if I'm going to maximize volume, if I'm going to do that through calculations of some kind, I need a formula that gives you the volume. So I'll just tell you that as a matter of fact, as a matter of geometry, then the volume of a box is the product of the width and the length and the height, which in my case is W times H. Okay, so there's our formula for the volume. That's the thing that we want to maximize. So we should start there always. If the question says, how do you maximize this or that thing, like whatever it is, you need a formula for whatever they're asking you to maximize or minimize, whatever the case is. Okay? All right, now, whenever we get to that point, this might have more than one variable in it. Like here in my formula, the variables are W and H. But when we do calculus, at least in beginning calculus, we only deal with one variable. Okay, so I need to reduce this to one variable, and so I try to find ways to use the other information that was given in the question to do that. And then I realized that, well, so far I've drawn a picture to represent what this is that we're dealing with. I've labeled it correctly. I've given a formula for the volume, but I haven't used this other criterion which says that the sum of the length, width, and height can't exceed 144 inches. Okay, so then we might think that, all right, well, just at its maximum then, W plus H would need to be 144. Okay, all right, I mean, in order to strive for getting the maximum volume, right? Okay, that's what it said, right? Those are the rules. It says, the biggest box you can have has a sum of length, width, and height not to exceed 144 inches. So I would think that for the biggest one possible, W plus H is 144. Now, W plus W is 2W. And if I solve this for H from there, and I get this, then I can take that and I can substitute it up here. And I'll reduce this to just having one variable. Okay, which is something we typically have to do in these types of problems. All right, now imagine if I do that. I've kind of drawn my direction of thought here. What would this become? V volume equals W squared times H, but h is 144 minus 2w. Now that would bring you to this. Okay, all right. That gives you the volume as a function of w, the width. Now that, I'll pause right here. I know we have a little further to go. That is what we're asking for in part A. It says, write the function of the volume of the box in terms of w, one of the edges of the square base. Okay, now I've done that. W squared is 144 minus 2w. That's where that comes from. Okay, now, all right, let's continue from here because, well, why do I think I could continue from here in order to find the maximum volume, like the biggest bag that's possible? Is that, well, if you want to find the maximum that V volume can take, you could just solve V prime is equal to 0. That's our technique that we use in these questions. That will find you the maximum or minimum of whichever one you're trying to look for. Okay. Now, I think, just looking ahead a little bit, if I'm going to find the derivative of this V prime, it would be a little easier. The rules would be a little easier to manage if I distributed the w squared in there. So I'm going to go ahead and do that. That's where this 144w squared minus 2w third power comes from. Okay. Now the rules of derivatives apply fairly easily to this. Like I said, now to find the maximum, solve v prime is 0. V prime, the derivative, bringing that power down, times 144, that's 288w minus, again, bring this power down, 2 times 3, 6w squared. Okay, set that equal to 0 because that's the derivative, and I'll factor it to solve it. Okay, and if I factor something and it's equal to 0, then either of those factors are equal to 0. So I get, on one hand, w is 0. On the other hand, 288 minus 6w is 0. W is equal to 0 doesn't really mean anything for us. A box with width at 0 would be non-existent. So forget that one. This one will solve. I'll get 288 over 6, or 48 inches. Okay, so the width of that square base should be 48 by 48. And we have part of the answer that we're looking for. It says, what are the length of the square and edge? Okay, square end edge. Just mean down here at the bottom. 48, okay? Then it asks for the height. Okay, so how would we get the height? So let's say that I now know that the width of that square base should be 48 inches. Now, the question asks me for the height also, as I showed you. I can use this and then look around to see if I have any formulas that tell you the height. So is there, like, just look around here. Is there a formula somewhere in my work that says h height equals, and then it tells you? That'd be this one, right? It says h height is 144 minus 2w. We just figured out what w was, and now, like, this is just the thing we need to put that number in and find out what the height should be. So to find, like, other things, like once you get your initial answer, w is 48 inches, if it asks you for something else, there will probably be a formula somewhere in your work to get there that will tell you, here it is for me right now. Okay, so all right, I'll say there it is. H is 144 minus 2w. With that 48, put 48 for w in, and I get that the height should also be 48. Okay, and it's not like that for every problem everywhere that there could be, these two numbers should match. It just happens to work that way this time. Okay, all right, so width of the square base 48, and how tall should it be? Also 48. Okay, all right, so the ideal biggest luggage that you can get in here with all the rules is 48 by 48 by 48. So it's like a perfectly square box. Okay, so height and width, both 48. Last question, what's the greatest volume? How large is the box? Now, I could tell you how large the box is in different ways. I could say, well, it's 48 by 48 by 48. And it's like there I'm measuring each side. But volume itself is a different measurement. And we can measure volume in lots of ways. Cubic feet, cubic inches in this case, gallons, liters. Those are all measurements of volume. Okay, so you want to know the volume in addition to this. Then I have, once again, I could look back at my work and say, is there a formula that will tell you volume? Okay, well, this one will. This one says volume is W squared times H, and I know both of those numbers. I could use that one. Okay, so let's just maybe do that, right? Okay, now for the volume is W squared H. Both those numbers happen to be 48, so 48 squared times 48. And if you, with a calculator, let's say, do that, it's 110,592 cubic inches. Okay, our units are cubic inches. All right, so then we get that last number like that. Now, the one thing that I didn't talk about of all these questions here is what's the interval of interest in the objective function. So in terms of vocabulary, the objective function is the name we give to the function that we're trying to find the maximum or minimum of. So if it says find the maximum volume that's possible, the function that tells you the volume is the objective function. The interval of interest, what that means is what can W, the variable in that function, be? Okay? And to make the case like that there are some limits here on W, I'll say, well, could W be, I don't know, like 1,000 inches? You know, is that reasonable? Is that within the realm of possibility? I say, well, how could it be? I mean, how could you have a bag that has a square base of 1,000 inches when the airline says that the sum of the length, width, and height can't be more than 144 inches? So this is obviously like outside of what's possible. So the interval of interest is just an expression of what's possible for the variable. Okay, and there are lots of ways that you could think about how to solve this. And I deliberated like how I would tell you to solve it, but how about this? Let's just look at the extremes. Okay, here's how I decided to do it. Say, okay, I got this function W squared is 144 minus 2W, all right? That's what we're working with. And I'll say, do you remember how we said that the width plus the height is 144? That the sum of all sides of the box have to be 144? So let's just look at the extremes of that. Like, what is the biggest? I want to focus on the height because there's just one of that there. And I want to tell you what the possibilities are for the width. So what's the biggest that the height could actually be under this condition, that the sum of all the sides is 144? So I'd say 144. I like to take it all the way to the maximum is 144. Well, say in that formula you let H be 144. Then you could cancel these 144s and get 2W is 0. Divide by 2, get W is 0. So this extreme for the height gives you this extreme for the width. Okay? All right. And then what's the other extreme for the height? Like, so I'm saying, like, push the height all the way up. You can only get to 144. All right. Push it all the way down. How far down could you push it? I guess to 0. Like, if I push it all the way down to nothing. So then I put 0 in for the height, and I get 2W is 144. Okay, and I divide by 2, I get 72. So that's the other extreme. So me pushing the height up and down to its extremes, I'll solve for the width in its extremes, 0 to 72. So would it make sense for the width to be less than 0 or more than 72? All right, so that's one way to figure it out. I thought that way was intuitive, so that's what I showed you. So that's what this is, an interval from 0 to 72. Okay, so there's our interval of interest, 0 to 72. All right, yeah, 73, that's kind of like 1,000. I mean, 1,000 is really extreme and really obvious that's just too big, right? And there's no way. But 73 is like that too. So in terms of this function and the conditions given, 73 might as well be 1,000. All right, so that's what the interval of interest means in the context of all of this. Okay, so I hope that helps you. As with all the videos, I try to end it with, if there's something else about this that we need to talk about, some other clarity needed, something else you're getting stuck on, let me know and I'd be happy to help.